Hey everyone, welcome back, and today let's solve Leetcode problem 300 titled Longest Increasing Subsequence. So we're given an integer array nums and we have to return the length of the longest strictly increasing subsequence. And a subsequence basically means that the elements are picked in the same order as they appear in the original array, but they don't necessarily have to be consecutive. It's basically the same thing as a subarray, it's just that it does not have to be contiguous. And in this case, it also has to be strictly increasing or in ascending order. So in example 1, we have the input array nums to be 10, 9, 2, 5, 3, 7, 101, 18, and we'd output 4 because that is the length of the longest increasing subsequence that is ascending, and that's going to be, in this test case, 2, 3, 7, 101, right? As you can see, we can't get any longer subsequences from there that are strictly ascending, and the way that would be structured is we take this 2, we take this 3, we take this 7, and finally we take this 101. Note that they aren't all necessarily consecutive, right? There is a 5 between the 2 and the 3. They just are part of one common subsequence that are strictly ascending, right? That's the main thing, or difference rather, of subsequences and subarrays. And that's why the length of that subsequence is 4, which that why is the output that we'd have for this test case. And in example 2, we have the input array nums to be 0, 1, 0, 3, 2, 3, and we'd output 4 because that is the length of the longest increasing subsequence. We can take this 0, and then take this 1, and take this 2, and then take this 3, which is going to be 4 elements in a subsequence of ascending order. And finally, in example 3, we have the input array nums to be 7, 7, 7, 7, 7, 7, 7. We only have one possible element to choose from, and so we can never increase or decrease. We can only say the same, and so regardless of which element we choose, we're only going to have a strictly longest increasing subsequence of 1, right? Because we only have the same element appear n number of times in our input array nums. So I'm actually going to be solving the follow-up as well, where it says that can you come up with the algorithm that runs in big O of n log n time complexity, right? And note that n log n is significantly faster than n squared, which is going to be the runtime complexity for our solution here. But honestly, it is pretty difficult, right? It's going to be pretty hard to come up with the n log n solution, and honestly, I would not expect your interviewer to ask you that in an actual technical interview. If you do, good luck, right? So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Alright here. Okay. So the challenge here is basically to track increasing sequences and basically choose the longest one. And we can efficiently solve this problem using dynamic programming, and this is actually a classic dynamic programming question that is a very common technical interview question at a lot of different companies, including the FANG companies, right? And we'll use dynamic programming to essentially avoid any redundant calculations being made for every iteration of our input array nums, right? So the way we're actually going to structure our algorithm is we're going to use a DP array, where DP at index I is going to store the length of the longest increasing subsequence that ends at index I. And we'll initialize every element, of course, in DP to be 1, because the smallest longest increasing subsequence, or LIS, that can end at any element is going to be just that element itself, or a length of 1. And for each element, nums at I, we want to compare it with all the previous elements, so basically every single nums at j for when j is less than I, and if nums at I is greater than nums at j, that means that an increasing subsequence using those two elements and maybe even more can be formed. And so in that case, we'd update dp at I to be the maximum value between its current value and dp at j, plus 1, or plus another value in that current subsequence. And at the end, we have to return the maximum value from the DP array, which is going to give us that longest increasing subsequence. And I'm going to refer to that as LIS because that is a mouthful to say every single time I want to really refer to that vocab. So in this case, I'm just going to initialize DP to be an array of 1 times whatever the length of our input array nums is going to be, right? Okay, and again, like I talked about before, every element in the DP array is initially set to 1 because the smallest possible LIS for any element is going to be just that element itself if we don't have any other strictly increasing subsequences or elements in future indices of our input array nums. And once I do that, now I can actually iterate through my input array nums, and I can do that using a standard for loop in Python for I in the range of the indices or the length of nums. Right, and our goal is basically for each I is to determine the length of the longest increasing subsequence that actually ends at this index. And to do that, we can have a nested loop. So for j in the range of I up until that index, right? Again, for every element at index I, we want to loop over all the previous elements from index 0 to I minus 1, where the variable j represents the index of those possible potential previous elements, right? Now we actually have to check if nums at index I, basically the endpoint of our current subsequence, if that's greater than nums at j, the previous elements, then we know that this can actually extend the increasing subsequence if it ends at nums at j, right? So again, basically we check if the current element nums at I is greater than any previous element in that iteration nums at j, and if that's true or that's valid, it means that nums at I can extend the increasing subsequence that ends at nums at j, and so therefore we'd have to update dp at index I to be the maximum value of course, itself, because we don't want to make it smaller, and dp at j plus an extra value, right? Because we want to include dp at I or nums at I into that value now. So we want to increase that subsequence from dp at j or index j by 1, right? So again, if that condition in the if statement above is true, we can update dp at I, where the value of dp at I is set to the maximum of itself, and dp at j plus 1, which again represents the length of the increasing subsequence ending at j extended by that current element nums at I to be part of that now to be part of that current subsequence, which is the very important or crucial line of this dynamic programming solution. And ultimately, outside of this nested for loop, we can simply return not dp at 0 or dp at n, but rather the max of dp, right? And basically how that works is after we process all of the elements, the reason why we can return the maximum value is because that would represent the length of the longest increasing subsequence given in the array, or in the given array, right? So if I were to submit this right now, as you can see, this would work, and this would be submitted, and it is pretty efficient. But like I said before, you can actually solve this in big O of n log n time. But before we do that, let's just discuss what this code again overall does and how it actually works with its runtime and space-time complexity. Okay? So again, this code basically builds up the DP array in such a way that DP at index I is going to hold the length of the longest increasing subsequence that ends at index I. And for each element at index I, our code basically checks all the previous elements to see if they are smaller. And if a smaller element is found at any index j, then the length of the subsequence ending at I is updated by taking the maximum value between dp at I and dp at j plus 1. And finally, the maximum value in the DP array is returned given the length of the longest increasing subsequence that basically ends at whatever the max of DP is, at whatever indice it's represented by. So again, for the time complexity, the outer loop runs in n times, where n is going to be the length of the nums array. And for each element, the inner for loop, the nested for loop rather, is going to run up to I times, leading to a total of big O of n squared operations. And so that's why the runtime complexity is going to be big O of n squared. And for the space complexity, this really only uses extra space, which is going to be the DP array, which has the same length as the input array nums. And so the space complexity is going to be big O of n, or linear time. Okay? So that's the solution for the n squared solution, which still should be accepted. It is still a very good solution to come up with. It's a great solution. But we want to solve the follow-up as well, which is, can you come up with an algorithm in big O of n log n time? Which, note that if you guys are familiar with runtime complexities, n log n is significantly faster than n squared, and in many different cases, it can make all the difference that you need to optimize your program. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so like we talked about before, all of this is a common dynamic programming problem. We can actually solve it in nlog time to, again, make it as efficient as possible and solve this follow-up, right? And the way the solution is structured is we'll basically use a list called, I'll just call it sub, that's going to help us track the smallest possible increasing subsequence as we iterate over the array. And binary search is going to be used to determine where each element from the input should be placed in that sub list. And this ensures that building the subsequence is actually done efficiently. And we won't store the actual subsequence, we'll just store the lengths needed to determine how long the LIS can actually be. Okay? So with that out of the way, let's just go ahead and dive straight into the efficient code. So I'm actually going to import a module called bisect here. And all of this is probably already imported in Leetcode because all the modules and dependencies are already pre-installed in your editor. I'm just going to do it for best practice. So the way we do this in Python is we'll use the from keyword. So we'll say from the module bisect, we want to import bisect left. And I think that's just the module name. There's nothing really else. But again, we're basically importing this bisect left function from the bisect module. And bisect left, if you guys aren't aware, basically allows us to perform a binary search on a sorted list, finding the position where an element can fit to keep the list in sorted order. And this helps us insert elements into the sublist in big O of login time, which is really efficient, right? Login is very good runtime wise. Okay, once we do that, now, once we actually import this module, now let's actually just loop through the input array nums. But before we do that, we want to actually initialize our sublist. I'm just going to initialize it to be an empty list, right, as denoted by these square brackets. And the sub is going to basically store the smallest possible increasing subsequence during every iteration, right? So once we actually initialize that subsequence, now let's actually iterate through the input array nums. So I'll say for I, or rather for nums, to make it a little bit easier, for num in nums, oops, change that to a colon, not a semicolon, right? And this variable num is basically going to take on each element from the input array one by one. And now this is where we can actually perform the binary search to actually find that correct position. And this is where the bisect left function from the bisect module is going to help us out. So we'll say I is going to be equal to bisect left, and we'll pass it as our parameter the sub and the num itself, right? So basically for each element num, we can use bisect left on that sub list to find the index I where num can actually fit. And if num is greater than all the elements in sub, I will be equal to the length of sub, basically indicating that num should be added at the end. And if num can replace an element in sub to form a better subsequence, I will be the position where it should actually replace, or where it should replace it. Okay? So now once we actually binary search on the num, we can check if I is actually equal to the length of the sub. And we know if that actually outputs to be true, we can append to our sub list the actual value num. Right, so basically if I is equal to the length of the sub, it means that num is larger than any element in sub, and in that case we can append num to the end of sub, increasing the length of the current subsequence in this iteration. And otherwise, if that's not the case, so in Python we'll just do else instead of else if, right? We'll just set sub add index I to be equal to num. Oops. Okay, we'll set sub add index I to be equal to num. Right? And basically what this says is if I is less than the length of sub, it means that num can replace the element at index I. And this helps us maintain the smallest possible values in sub and essentially optimizes future subsequences in future iterations. And ultimately, outside of this for loop, all we have to do is simply return the length of the sub. And so unless I made any syntax errors here, this should be accepted. So let me just run this program here. And as you can see, this is just about as efficient as you can get. So to better explain line 11, we basically return the length of the sub list, and that's because since sub stores the smallest possible increasing subsequence, its length basically gives us the answer to our problem, the LIS of the input array nums, right? So basically, to explain what the code does overall, again, if you guys are still a little bit confused, we basically loop through each number in the input array nums, and for each number, we're basically using the binary search algorithm using the bisect left module or function to determine its position in the sub list. And if the number can actually extend the sequence, we can append it to the sub list. And if it can replace an existing element, then we can replace it to maintain the smallest possible subsequence. And finally, the length of the sublist will basically give us the length of the longest increasing subsequence that's present in the input array nums. So again, obviously this is going to have a time complexity of big O of n log n, right? Because again, each call to the bisect left function is going to take big O of log n time because it performs a binary search. And since we iterate over the array of length n, the overall time complexity is going to be big O of n times log n. And for the space complexity, we're going to use the sublist to store elements, which in the worst case could be as large as the input array nums. And so therefore, the space complexity is going to be big O of n. We're just using this extra space or list of sub, right? Which at worst can actually be as large as the input array nums. So basically, the solution efficiently finds the length of the LIS, or longest increasing subsequence, in big O of n log n time using a combination of binary search and list replacement. And this is obviously much faster than the traditional dynamic programming approach, which takes big O of n squared time. And that's basically it. So thanks for watching, guys. If you found this video helpful, please make sure to like, subscribe, and comment down below. And without further ado, I will see you guys in the next video. Bye-bye.